You'd think more features always help. More columns in your data, more dimensions in your vectors, more signal for the model to learn from. It doesn't work that way. Past a point, more features make your model dumber, slower, wronger. And it's not a bug in the algorithm, it's a fact about geometry. The math is brutal. Richard Bellman named this in 1961. He called it the curse of dimensionality. And it's one of the deepest reasons why just add more features is the classic beginner mistake in machine learning. Today, what the curse is, why it happens, and why NLP embeddings dodge it. Last video we talked about hidden Markov models with discrete hidden states, a handful of phonemes, a handful of tags, small state spaces, very manageable. Now we jump to the opposite regime. What happens when your representations are big vectors? Thousands of numbers per word, millions of parameters, space that our brains cannot picture, and what the geometry does to you there. Here's the puzzle. In 2 dimensions, geometry behaves the way you expect. In 3 dimensions, still mostly. In 100 dimensions, everything you know is wrong. Volumes explode, distances stop mattering, nearest neighbor becomes meaningless, and every naive machine learning method silently breaks. Question is, how does NLP survive that? Today's 3 beats. First, what the curse actually is. Volume explosion, empty space, distance collapse, 3 symptoms, 1 cause. Second, why nearest neighbor breaks, and why every ML method that leans on distances breaks with it. Third, why NLP embeddings still work anyway. The manifold hypothesis, plus PCA, t-SNE, UMAP as escape hatches. Beat 1. Volume explosion. Take a unit cube. In 2 dimensions, area equals 1. In 3, volume equals 1. In 100 dimensions, the unit hypercube still has volume 1. But here's the trick. Almost all of that volume lives in the corners. The middle is empty. In 100 dimensions, if you sit at the center of a unit cube and stretch your arms out to length 1/2, you touch essentially nothing. Symptom 2. Empty space. To cover a d-dimensional space with samples, you need exponentially many, not linearly, exponentially. To have 1 data point per unit in 10 dimensions, you need 10 billion samples. In 100 dimensions, you need more samples than there are atoms in the universe. Your dataset is not big. The space is insane. Symptom 3. Distance collapse. In high dimensions, the distance between any 2 random points becomes roughly the same. Nearest and farthest neighbor blur together, which sounds impossible. It's not, it's a specific theorem, and it kills the whole idea that similar things are close together in feature space. Beat 2. Consequences. In classical ML, a lot of methods lean on distance, being a meaningful signal. K nearest neighbors, kernel methods, radial basis functions, density estimation, naive clustering. Every single one starts wobbling once your feature vector has more than about 50 dimensions. Add 100, add 1,000. It gets worse. There's a related pain point. Classical statistics wants more data than parameters. Rule of thumb, 10 times as many. If your model has 10,000 features, you want 100,000 examples minimum. In NLP, you routinely have millions of features and hundreds of thousands of examples. This is called the P bigger than N regime, and every statistician trained before 2010 will tell you not to do it. Every deep learning practitioner does it anyway. Which brings us to the big question. How does modern NLP get away with 768 dimensional word vectors? 4,096 dimensional embeddings, attention with 12,288 dimensions per layer. Every one of these should be cursed, and yet they clearly work. So what's going on? Beat 3. The escape hatch. The manifold hypothesis. Real-world data doesn't fill up its high-dimensional feature space. It lives on a much lower-dimensional manifold embedded inside that space. Think of a crumpled sheet of paper floating in a room. The room is 3-dimensional. The paper is 2-dimensional. The paper is where all the interesting stuff is. Data does the same thing. The manifold hypothesis is why word embeddings work. There are thousands of English words, but the semantic relationships between them live in something like 50 to 100 effective dimensions. The 768 numbers in a BERT vector are mostly organization, not information. And that's why cosine similarity in embedding space actually tracks meaning, even in a space where distances should be meaningless. Which brings us to dimensionality reduction. The workarounds: PCA. Find the linear directions with the most variance and keep only those. t-SNE. Nonlinear, preserves local neighborhoods, great for visualization. UMAP. Like t-SNE but faster, and preserves more global structure. When you see a beautiful two-dimensional plot of word embeddings, one of these three algorithms just projected it down from many more dimensions. 3 takeaways before the quiz. 1. High dimensions break intuition. Volume explodes into corners. Space stays empty. Distances collapse. Bellman called it in 1961. 2. Distance-based ML methods break above about 50 dimensions. Nearest neighbor first. Kernel methods next. Naive clustering right after. 3. NLP embeddings dodge it because data lives on a low-dim manifold inside a big space. And PCA, t-SNE, UMAP let you see it. Quiz 1. In a 100-dimensional space, what happens to distances between random points? A. They become widely different. B. Nearest and farthest neighbor, distances collapse toward the same value. C. They shrink to 0. Or D. They follow a normal distribution. B. They collapse. It's a specific theorem. In high dimensions, the ratio of the max distance to the min distance in a random dataset approaches 1, which means its closest point and the farthest point become indistinguishable, which means nearest neighbor as a concept stops making sense. Quiz 2. Why do modern NLP embeddings work despite living in hundreds of dimensions? A. They cheat with low precision. B. The manifold hypothesis. Real data lives on a low-dimensional surface inside the high-dim space. C. They ignore geometry. Or D. They don't work. It's marketing. B. The manifold hypothesis. The 768 dimensions of a BERT vector are mostly organization, not information, meaning lives on something like a 50-dimensional sheet inside that space. That's why cosine similarity still tracks meaning, because meaningful pairs sit close on the sheet, not close in the ambient space. Quiz 3. Which of these is a standard dimensionality reduction technique used in NLP? A. Random forests. B. Gradient boosting. C. PCA, t-SNE, or UMAP. Or D. Bayesian networks. C. PCA, t-SNE, UMAP. PCA is linear. t-SNE and UMAP are non-linear. Every gorgeous 2D word embedding visualization you've seen was projected down with one of these. They're not the model, they're the microscope for looking at what the model learned. Back to the puzzle. The curse is real, and it explains why classical machine learning kept hitting a ceiling. The geometry of the feature space fought back. The escape wasn't more data alone. It was noticing that data lives on a manifold, which is what deep learning implicitly exploits. Next video, we drop from geometry down to probability. Bayes' rule. 5 symbols, everywhere. Next time, Bayes' rule. 5 symbols that show up in every spam filter, every speech recognizer, every machine translator, and the meme that lets you never forget them. Prior times likelihood divided by evidence equals posterior. 8 minutes. Hit subscribe.